on where you are, to all our participants to this first webinar being organized by International Commission on Irrigation and Drainage. Myself, Avinash Chantyagi, Secretary General of International Commission on Irrigation and Drainage. This is a professional organization which brings together agriculture, water management professionals all around the world. I would like to just very briefly introduce you to what ICID, the ICID activities with the 3 slides. Just to give you an idea, we are a professional network which consists of experts from 60 member countries, which represents 90% of the total irrigated area, and our vision includes water secured world free of poverty and hunger through sustainable rural development. Take some time. Our ICID mission is to work together with all stakeholders towards sustainable agriculture water management through interdisciplinary approaches to economically viable, socially acceptable, and environmentally sound irrigation, drainage, and flood management. The organization has set 6 goals to enable its members to meet the new development challenges, which are listed here. I will not take time to read, but these are what we are trying, and one of the most important one is to facilitate capacity development among the countries. Now, this is the first webinar in the series being organized by International Commission on Irrigation and Drainage. And first of all, I will like to invite Dr. Syed Narezi, Chair of TUSAB International, Iran, and the current President of ICID, to give a brief background of this webinar series being started by ICID. Dr. Narezi.
Okay, welcome. Welcome to our first webinar. Dear colleagues, friends, participants, ICID is a professional organization engaged in sharing information and knowledge on various facets of irrigation and drainage since 1950. Over the years, the focus of the organization has slowly moved from development and maintenance of irrigation infrastructure to more holistic contribution towards development, management, and application of irrigation and drainage as a tool for sustainable rural development. With the number of stakeholders engaged in agriculture water management increasing, the dissemination of information and knowledge generated by various technical working groups of ICID has become that much more challenging. For sharing this knowledge across a wide spectrum of users, ICID has taken the initiative to make use of information and communication technology to reach out to the variety of stakeholders across the globe. Some of the services that have been refurbished or introduced during the years are new ICID websites, integrated library management system, e-publication, and virtual communication tools like web conferencing and teleconferencing. Today, we are implementing this new initiative through ICID webinar services. To begin with, we start with the topic of water use efficiency. This will be followed up by webinars, about 1 per month, on various topics related to modernization of irrigation systems. The theme for our next Congress scheduled for October this year in Mexico. Once again, I welcome you all, and I'm sure you will enjoy this session. We will be happy to receive your feedback to improve this webinar series. Thank you.
Thank you, Dr. Narezi. The topic of today's webinar is water use efficiency. And we have with us Engineer Felix Renders, a professional engineer registered with the Engineering Council of South Africa, with vast experience in irrigation and drainage engineering at Agriculture Research Council's Institute for Agriculture Engineering, who will be delivering the webinar. Mr. Felix plays a pivotal role, especially in the coordination of irrigation engineering research, development, testing, design, and training, and mentoring. He is a regular guest lecturer at the UNESCO IHC also. However, before I invite Engineer Felix, I would like to introduce another eminent personality, Dr. Chris Perry, an authority on the subject, who has worked for World Bank on irrigation and water resources projects for more than 20 years. He was subsequently heading research at the International Water Management Institute and was editor-in-chief of Agriculture Water Management for 5 years. Over to you, Dr. Chris Perry.
Well, thank you very much for that introduction. It's a privilege to introduce this discussion and really congratulate ICID on the initiative in starting this important conversation. As the President, looking forward and questions which we hope perhaps we can answer, because it's really important issues. All of us participating today show in how we can move towards sustainable water use, especially in areas where aquifers already are falling, where rivers are and polluted, and yet there is demand for irrigation and other water services. Those demands are expanding. No doubt we all have unique experiences to bring to the discussion, because almost every water situation has its own special features. One thing we all face: in the future we shall have to manage water resources better and more productively. And we, whose farmers, engineers, administrators, politicians, not to mention academics, researchers, and the international financing agencies. Much has been written and said on the topic of better water resources management in international conferences and papers and reports. Lots of words, but little basic consensus about what actually needs to be done. Felix's contribution will clarify at a very practical level what is happening in South Africa, but first a few words of background. The most important change in the context of water resources management over the last 50 years or so has been the emergence of competition for water at basin scale. What we divert from a river or pump from an aquifer in one location has implications for other users and other sectors in other places. This new reality means that the perfectly legitimate objective of local water management, local water managers, be they individual farmers or project managers or water supply utilities, they have their local objectives to better serve their local needs. But these interventions now have implications for other users. This means that we need a common terminology for describing the impact of water use and to a water supply. Indeed, meanings may even change between for use during the dry season. Then our perspective was too complex. So what prompted this discussion now some 10 years ago among the ICID community to reach a consensus on how to at least improve our analysis of these issues. As I think Felix's presentation will demonstrate, we discover new insights when we apply this approach. We understand things better, and we make better decisions as a result. Thank you for joining. Now over to Felix.
Thank you very much, Chris, for the kind words and the introduction from Secretary General. Good morning or afternoon or evening to all the people listening in from all over the world. So I will kick off with this very first seminar, webinar, in terms of the topic water use efficiency. As Chris has outlined, it's a topic being discussed lately in depth, and in South Africa we did also a lot of work in terms of how to address that. So my talk is about efficient irrigation by applying a water balance technique. So what you'll be seeing the next couple of slides is, of course, some introductory words, the water balance approach, the application of the water balance approach, the results, and then some concluding remarks. And Secretary General, I just wanted to confirm, can you see the slides? It seemed to me you can see the slides.
Yes, we can see the slide. Please go ahead.
I will go ahead. So just as an introduction, the importance of water. Water is the key to food security, because as we know, without water, crops simply do not grow. Water is not just for primary production, it plays a vital role at all stages along the agricultural value chain. And water for agriculture connects us all together. In times of scarcity, we all have a responsibility to use water wisely, efficiently, and productively. And we need to be more water smart. And in terms of the agricultural water management as defined by the Comprehensive Africa Agricultural Development Program, is the continuum from rainfall management through to irrigation for food production, and it includes field water conservation practices, water harvesting, supplemental irrigation, groundwater irrigation, surface water irrigation, and of course drainage. So if one look at the water balance approach, then one see it is for a project that is complex set of inflows, outflows, consumptive use, and recycling of water. So in essence, we are talking of the withdrawal for irrigation use, either from a stream, groundwater, or storage, and then there might be some storage chains, some consumed fraction. I will define it a little bit later, and then the non-consumed fraction. So if one look at the water balance framework, which was defined by Chris Perry, and that is a framework that was adopted by the International Commission on Irrigation and Drainage. And the basis for a framework is, of course, the withdrawal for irrigation water, as I've explained earlier, from streams, groundwater, or storage. And then you might have some storage chains. And remember the symbols SC, because we are going to utilize that later. And that means flow to or from aquifers, in-system tanks, reservoirs, etc., with no significant change in water quality between the in and outflows. Then you get the consumed fraction. Now the consumed fraction, there are two parts. The first part is the beneficial consumption. And remember BC, that is water evaporated or transpired for the intended purpose, e.g. crop transpiration. Then you might also have the non-beneficial consumption. Water evaporated or transpired from purposes other than the intended, e.g. evaporation from dams, riparian vegetation. You'll see the one is in green, the other one is in red. So we would like to optimize the beneficial consumption. Then the third part is the non-consumed fraction, And there we also got what we call the recoverable fraction, RF, and water that can be captured and reused, e.g. drainage from water from irrigation fields. And then there's the non-recoverable fraction, water that is lost for further use, and that might be flows to saline groundwater aquifers, flow to the sea. So with that in mind, we will be looking at how this can be applied in an appropriate way. So what we did in terms of research over a period of 4 years, we developed what we called a water management infrastructure. And we defined the different water management levels. You will see water source, the bulk conveyance system, irrigation scheme, and the irrigation farm. So the infrastructure component that we are talking in terms of water source and bulk conveyance might be the reservoir, the river, or the canal. And the irrigation scheme might be an on-scheme dam, a canal, or a pipe, or the water supply can come from an aquifer. And then on-farm is, of course, the on-farm dam, on-farm pipe or canal, and the infield irrigation system. So defining the efficient use of the irrigation water, we are talking from the water source. And as you know, we came out of a drought in South Africa, and this picture was taken last week when one of our major dams, all the sluices were open. But that is then defining it from the water source to the irrigation scheme to the field where the crop is actually growing. So by taking that into account, one can then look at the efficient use of irrigation water and defining how the efficient use of water can be done. So from the water source again, we are talking to the irrigation scheme, to the farm, to the field, to the crop, and there might be what is often referred as losses. That is why it is in brackets or in hyphens. So on-scheme losses, on-farm and infield losses. So ensuring that most of the water taken from the source reach the intended target, the crop that we would like to grow, and by minimizing the losses along the way, we can use the water balance approach. So implementing the water balance approach, and I got here a framework that was also utilized and developed in Australia by Purcell and Curry, and you can see from the scheme to the farm to the on-field in terms of finally the yield. So you can apply it at the different levels during design and of course during management. So unfortunately, historically, reporting of irrigation efficiencies such as application efficiency, system efficiency, distribution efficiency, transportation efficiency, etc., have resulted in the diminished understanding and scrutiny of the source of causes of losses. There's a widespread illusion that efficiency is fixed by the type of irrigation infrastructure used rather than the way a particular system has been designed and managed. In the past, improving performance and efficiency was incorrectly only associated with an upgrade in infrastructure or change in irrigation system. So let me then just quickly touch on the two principles, water use efficiency and water productivity, that we are all on the same page. Water use efficiency, that is where efficiency can be any process, and use, it is normally defined as the useful output over the total input times 100. So note, output and input need to have the same units. And we normally express it in agriculture as a percentage, and that is applied to the plant that is effectively taken up by the plant, that is not lost due to drainage, bare soil, evaporation, or interception. In the example, if we apply 10 millimeters of water, there is 2 millimeters lost through drainage and only 8 millimeters utilized by the crop, then the efficiency, water use efficiency might be defined as 80%. If you look at the concept of water productivity, productivity is in general refers to what you can produce from a unit of input. And note again, input and output don't need to have the same units. Water productivity in agriculture is the crop yield produced per unit of water supplied, and sometimes one talk about so many kgs or tons per cubic meter of water. Modern agriculture aims to increase yield production per unit of water used. So if one look at efficient use of irrigation water, the water balance approach is more flexible than calculating ratios. It takes into account the intended destination of water, taken from a source, and how the water is used along the way. It encourages a better understanding of water management at all levels. And the water balance framework are recommended by the International Commission on Irrigation and Drainage, as published in an article by Chris Perry in 2007 already. So if one look at the framework and we allocate typical irrigation system components to that, you'll see again the darker blue is the dam, the river, and the canal bulk conveyance system. The lighter blue on-scheme components, and the light blue is then the on-farm situation. So just as an example, the very first one, the water balance framework system component is a dam reservoir, and the inflow of water into the system component is the total amount of water released from storage. And so you can define the inflow to the different areas that are under investigation or that you would like to look at. So if one allocate typical infield irrigation system components, just taking that last part, so the possible water destination from the infield irrigation system component, the framework classification, remember the storage chains, the beneficial consumption, non-beneficial consumption, the non-recoverable fraction and the recoverable fraction. And then you can define a desired range or percentage of inflow. So for instance, if you take interception, which is normally unavoidable, that is defined as a non-beneficial consumption, and you define it should be less than 5%. Or operational losses, unavoidable in some cases, non-recoverable fraction, you can define it as then less than 5. So you can build up your framework from that. So how do we apply that water balance approach? First of all, you need to compile it with a few simple steps to achieve a improved water use efficiency. First of all, you identify the appropriate level of application. You identify the water management infrastructure, identify the boundaries that we've just discussed, define the inflow, finalize the list of possible water destinations, and then lastly set the allowable range of threshold values. So I took an example that we did some work on, and that is one of our biggest schemes in South Africa. That is the Gamtoos irrigation scheme. It's located in the Eastern Cape and has 7,431 hectares of scheduled irrigation area. Water allocations are 8,000 cubic meters per hectare, and there are approximately 170 farmers on the scheme receiving water from the Kouga dam. Now, water is distributed with a canal network with automatic gates, and water meters are used to measure water. Very important, measuring of the water is distributed through pipelines to the farmers from the canal network. Irrigation systems used include center pivots, drag lines, micro, drip, and traveling guns to irrigate a range of crops, but mostly citrus, about 30%, and then you'll also see vegetables, pasture, coffee, tobacco, soybeans, and canola. So that is the summary of the scheme. The Kouga Dam with 7,431 hectares with the canal, supplying it from the dam, and then through a pipe system with the water meters, with an allocation of 8,000 cubic meters per hectare to the 170 farmers, and with all the different types of irrigation systems. Water are measured by means of probes in the soil profiles, and then of course automatic weather stations collecting data to calculate what is the amount needed to do proper scheduling of the water. So the board of the Gamtoos is continuously upgrading the scheme and has in the last 9 years succeeded in improving the management of the main canal. There is an ongoing process of repairs to siphons on the main canal in conjunction with the Department of Water Affairs, as the scheme is strategically important in its role as co-water provider to one of our metropolitan cities, Port Elizabeth, in the Eastern Cape. So first of all, step number 1, identify the appropriate level of application. So the correct agricultural water infrastructure usually includes the following components applicable at different levels of water management: an infield irrigation system, an on-farm water conveyance system, and on-scheme water distribution system to convey that water to the farm edge. So secondly, identify the water management infrastructure as we have discussed earlier. The applicable infrastructure is then identified according to the water management infrastructure. So are we talking of the water source, the bulk conveyance, the irrigation scheme, or the irrigation farm? And that can then be defined and identified. Then identify the boundary. When defining boundaries for water balance areas, it is necessary to define both the spatial boundaries as well as the temporal related to time boundaries. So in this sketch, you can see the riverbank, the bottom of the river, the outflow, and the inflow section. So very important how you define those boundaries. So the spatial boundaries in our case study was the infield application system. You can see the upper boundary is the crop canopy. The lower boundary is the bottom of the root zone, and the horizontal boundaries is, for instance, the field edges. If you go to the river system, at the bottom, it might be the water surface, the bottom of the river, all the river inflows, outflows, and sides. So that is your spatial boundaries. And then, of course, your temporal boundaries of the water balance are determined by the purpose of which the balance is done. So it could be an annual investigation, where you would like to look at a 1-year period, or in some cases, such as at field level, the time scale might be reduced to the length of a season for a specific crop, or a daily soil water balance can also be done for a specific reason, such as irrigation scheduling, as an annual balance at this level will be useless. So defining the inflow, the source of the water entering the system component must be specified, as this is usually the parameter which is being scrutinized by compiling the water balance. In order to compile a credible water balance, the flow volume or flow rate at the entry point of the system component must be measured and quantified. The more often this can be measured, the greater the accuracy and the reliability of the data. Continuous measurement should be the aim of any measurement system. And then finalize the list of possible water destinations. So where's the water going? When drawing up the water balance, all water entering the water management level as inflow should be allocated to a specific destination within or exiting the water management level boundaries. And you can see there might be unlawful abstractions, there might be deep seepage losses, there might be riparian vegetation, or evaporation losses. So that must then be also, that list must be finalized. And the specific situation must be inspected for which the water balance are being compiled, and all the possible water destinations must be identified. Each destination must then also be classified in terms of the water balance and framework, the beneficial consumption, non-beneficial consumption, recoverable fraction, non-recoverable fraction, and storage change. Then one set the allowable range or threshold values. And the allowable range or threshold values are the benchmarks according to which the water balance is assessed. By comparing the actual value entered, which you have measured, for a specific water destination as a percentage of the inflow with the benchmark, decisions can be made as to whether action is required to reduce water reaching the destination. Setting these values are therefore of great importance. So if one look at the results, one can then get the collected data in our case, we looked at the seepage, and that is a very difficult one to determine. So from literature study and from the different type of soils and canal lining, it was determined that it is approximately 1.2 liters per second with 1,000 square meters of wetted canal. Secondly, evaporation was calculated on the basis of the actual measured daily plan evaporation figures, together with the automatic weather stations. Losses were observed but couldn't be quantified. It included canal spills and unlawful use. And then the combined results of the measurements, together with estimated confidence intervals for various components, are shown in the next table. But this was typically the results that we gathered. You can see the inflow, the usage, the gross losses, and then there's also some other specified losses with more detail. You can see for the month of December, January to February, cubic meters of water that entered that specific area was 1,261,844 cubic meters, and the total is then 3,907,903 cubic meters, and the usage was then 3,281,570, which is then 84% of the inflow. The gross losses was then 16%, and you can see evaporation that was calculated, the seepage that was also calculated from that 1.2 liters per second per 1,000 square meter of wetted canal width, and that is then a total of 4%, and then evaporation from the dam could be calculated, and then seepage also from the dam. With your confidence index, minimum, maximum set, one then can utilize, and we have developed an Excel spreadsheet. There's also an excellent one that was developed by IMWI in terms of your capturing all your inputs, and then you start doing the calculations. And by using this spreadsheet, the final water balance was compiled by combining the inflow and water destination values. And there you can see the farm edge, on-farm storage distribution system of there's that value that was utilized with the 84%. There's the total right at the bottom, the 100%. With the evaporation from the canal, which was 15%, seepage in the canal, 30%, or the confidence value, sorry, that's confidence values. And then the percentage of the inflow is then calculated according to those figures. And with investigation, then of course, with your desired levels that you have set for yourself, you can then say, but it exceeded the desired level in terms of the seepage in the canal. So we need to pay attention to the seepage in the canals. The others are still looking fine, but that is how you can go about evaluating and making sure that where is the areas that you would like to decrease the outflow or the water going to the destination. So from that, we also did some work on a total of in-field irrigation systems, where we evaluated a total of 75 irrigation systems to determine the system efficiency for design purposes, looking at the systems and determining that values. And we also applied the water balance methodology. So the irrigation system, you'll see the different systems as defined from drip to microspray to center pivot, down to flood to sprinkler and traveling gun. And there's the non-beneficial spray evaporation and wind drift in terms of the values that were measured in terms of the different areas, infield conveyance losses that you might have in terms of flood, mainly line canal supply or earth canal supply, and then filter or minor losses that you can define with the total losses. So we defined a default system efficiency of net to gross values, and that is what mainly is utilized by designers when designing a system to go from net values to gross values. So that also support the irrigation system approach in terms of the system efficiency values that we have developed. So in conclusion, a water balance approach of measure, assess, evaluate and improve promotes an investigative approach to improve irrigation efficiency, and the adapted water balance framework assist managers and designers alike to apply it at any level to improve system performance. I thank you.
Thank you, Dr. Felix, for that very interesting talk. We have a couple of questions. One question is about the role of ICID in bridging the huge gap in capacity development in Africa. I have passed it on to Dr. Felix. I also have another question regarding the role of storage in irrigation. And I have requested Dr. Said Narizi to give his comment. There are a couple of questions regarding the availability of this particular presentation. This is for the information of all who are attending, that we are recording all this presentation, and this will be available on our website, www.icid.org, where you can in the section which is dedicated to webinars, and you can always find those presentations. Before the presenters, before Dr. Narizi and Dr. Felix answer this question which I have forwarded to them, maybe I would invite Dr. Chris Perry to give his comments. Is there any? Chris?
Well, thank you. Can you hear me?
Yeah.
Yes.
You can. Yeah. The main comment I would make is that when they have been doing in South Africa, the first thing it is very complicated. It seems to require a lot of information and so on. To gather this information, we have to make estimates of the information that we don't have, our best estimates, because that is the only way we can identify the priority areas where we can intervene and make things better. And the fact that we may have large confidence intervals on some of the data and other data we just simply have to guess should not put us off making a start. Because as you begin to refine the data, you ask better questions and you come with solutions that you probably they're doing.
Okay, I think that was slightly, the voice was not clear, but maybe we'll have to bear with this. I also have, again, before Felix, you answer that, I also have Mr. Bonghul Lee, who has raised his hand, and perhaps he would like to say something. So I am unmuting Dr. Bonghul Lee.
Avinash, would you please let me repeat your question, which I'm going to respond. What was the question you are going to put to me?
Okay, I will read that out to you, but I have just unmuted Mr. Bonghul Lee. Mr. Lee, are you there?
Yes, can you hear me?
Yes, please go ahead.
I mistouched my system, so I don't have any questions, sorry.
Okay. Thank you.
Maybe just to fill in what Chris Perry said, and that is true. He said it is a complex approach. Of course, one need to look at estimations and as many as measurements that one can do. That will enable you, of course, to develop that water balance and do the necessary evaluation. But it is true, as Chris Perry outlined that yes, it is not always that clear, but as soon as you start defining start at a infield basin and then work your way towards the bigger parts in terms of the bigger schemes.
Okay, maybe Felix, you can answer the question which is posed there. Can you see that question from Amali?
Yes, you said about the capacity building in Africa.
Yeah, that's right.
Yes, I think ICID has a particular role internationally to play and to bring everybody on board. Africa is one of the continents where we do not have a huge participation, and through the networks of SARIA, that's the Southern African Regional Irrigation Association, we managed to get the SADC countries on board. We are going to have a meeting in about 3 weeks' time here in South Africa, where we try, and we've already signed memorandums of agreement, the same in Northern Africa in terms of ARIT, which is also mobilizing and bringing people together in terms of the involvement of African countries into the ICID family. And excellent support has been provided by ICID in the past, both in the southern side as well as in the northern side. Last year there was a big conference Cairo, well, not in Cairo, it was at the Aswan Dam, where they have the 4th African Regional Conference, and ICID supported that. And the same thing happened down 2 years ago, where ICID also supported initiatives in terms of capacity building within the SADC region. I think ICID is trying its best, but we also need the collaboration and buy-in from the African countries to really come on board, to make a commitment, and also join the ICID family.
Thank you, Felix. Dr. Naredi.
I've got a question first from Felix. Can I ask a question?
Yes, please, go ahead.
Yes. What is really these days, what is important to our colleagues in the Middle East, particularly in Arkan, Iran, and they are not very sure that this seepage or deep percolation, which you have showed that, how you can make sure that this deep percolation will recharge the groundwater and again it is reused. How can we make that clear? What part of this seepage is lost? What part of the seepage or deep percolation or percolation reaches to the groundwater for reuse?
Thank you for that question, Sahid. Yes, seepage is a difficult one to define and also to measure. But in essence, it is not really water lost. There are return flows, supplementing the aquifers, and maybe downstream that could be assessed or accessed in terms of wells or boreholes. But as I've indicated also in the study that we did, it is very difficult to measure that and also to determine what is the movement and where is that movement towards what source deep down in a secondary compartment or aquifer. But one must not see that always as a loss. And maybe Chris Perry can also give some idea of comments on that.
That the default assumption historically has been that if it a loss and it is gone. And from farmers' perspective, and probably from the irrigation perspective, looking locally, that is true. But it becomes very dangerous when we look at that as the default assumption. And the safer assumption is that it is bearing that somewhere is a recoverable or unrecoverable. We have to
Okay, thank you. Dr. Narizi, the question for you is largely a comment, in fact, and generally the commenter is Mr. Somdat Gupta, and he is talking about that requirement of storages in India and how this should be addressed. Although it is not a question directly related to the item to this webinar, maybe you would like to just say a couple words.
If he means that if how the storage and dam construction is necessary for irrigation or not,
Yeah.
if that is the question, it is, you know, that these days there are a lot of people and organizations are against dam construction in the world, because this seems it is going to destroy the environment, and it is very anti-environment consequences. But however, we believe that we cannot, particularly when the climate is changing in the central part of Asia, in Middle East countries, we have to store, to be able to have some storage capacity for irrigation. Otherwise, we cannot rely on the river flow, which is changing by the time from the year to another year, and so we cannot have any permanent irrigation system relying only on the river discharge and updated or river flow. But however, groundwater can be used as a part of backup to that. So I believe that we have to use groundwater and surface water together in order to be able to be sure that even when the river flow is low, we can have some backup by groundwater supply. However, if you ask me what is my vote to the reservoir, I would give a positive vote to the small reservoir, one for annual control of the river flows, not storage from one year to another, but to support irrigation systems.
Thank you, Dr. Narizi. We have one more question. This one is from Upali Masenge. And Felix, I have passed on to you. Can you see it in your question box?
Let me just plus.
I will just read it out in the meantime. How do you account non-processed beneficial evapotranspiration? This ET, such as from homestead in some irrigation systems, have substantial environmental, social, financial impacts. So this is a comment, but I hope you can answer that question and give the comment.
That first part, Avinash, it is the non.
How do you account non-processed beneficial ET? And this ET, what she is mentioning, is from homestead in some irrigation systems which have substantial environmental, social, and financial impacts.
Yes, that's a difficult one.
Can you pass an example? we haven't met for some years. What can you just give an example of what you mean? It's quite a technical definition you've given.
Okay, I will flash it to you also. Just a moment. Please. This is again. I'm just for other benefits and other listeners. How do you account non-process beneficial ET? This ET, such as from homesteads in some irrigation systems, have substantial environmental, social, financial impacts.
I am still myself not clear what is a non-process benefit.
Is Upali on the line? Upali, can you please raise your hand if you are on the line now? We can assign to you if you can explain. Upali, I have unmuted you. If you can please explain your question.
Yeah, see, what I meant here is you basically, these are the water recovered from seepage, the groundwater, and then evaporated through, home gardens, such as in, in Sri Lanka there were some studies, and it shows that non-processed ET is somewhere around 20 to 30% of the total water supply, total water diverted. So if you exclude that part from your equation, you are not really accounting the total, basically you are not doing the total water counts.
Do you mean that evaporation, not ET?
Yes.
Evaporation.
Evapotranspiration, both. Not
transpiration.
See, what you get from, I mean, I think if I understand well about Chris Perry's water accounting techniques, that's another part of the equation that is missing in Dr. Pilik's water accounting part.
Shall I say something, Avinash?
Please go ahead, sir.
I believe that evaporation, most part of the evaporation from the field is not productive and it is considered a loss. But there are argued that some evaporation from the bare land may assist through the cooling of the crop. Some may be helpful or useful. But I believe that it is better. We are better off to consider all the evaporation from the bare land as losses, and then we bring technology to reduce the evaporation as far as possible, which is considered a loss. This is my view.
Thank you. I think we had good discussion. Unless there is somebody else who wants to bring out any point, we can close. But
can I just add to that?
Pardon, please?
Can I just add to that comment about evaporation from Dr. Naizi? There's a very interesting study done by IRRI in North India by Liz Humphreys and some others on the relationship between evaporation and the total of evapotranspiration. And what they discover is for the field crops, so the rice, the wheat, and the sugarcane, where the canopy closes, any decrease in evaporation is matched by an increase in transpiration, so a zero-sum game. But, as you say, if it is bare soil and there's not a microclimate around the crop, of course it is a loss. But that typically is for vineyards and for orchard crops and so on, where you get large bare areas between the canopy of the crop.
Yes, thank you.
Thank you very much. So thank you, gentlemen. Thank you very much for joining. First of all, Thank you, Mr. President, for making that introduction. Thank you, Felix, for your efforts. Chris, thanks again for bringing out all your expertise to make this webinar successful. I also thank all the participants. We have about 45 participants as of now. Thank you very much. We look forward to your feedback. So please let us know through your emails how you feel the webinar went, what you would like to see in the next webinar in this series. And you can always visit our website, ICID, www.icid.org, where you can go to our webinar page. There you will be able to again see and go through this particular the recording of this particular webinar, and also will be able to find the schedule of other webinars which are in line. So with that, we once again thank everybody, and really I'm thankful to all of you for joining us. Thank you very much.
Okay, thank you. Thank you, everybody. Let's hope for the next one. Go for the next one.
Okay.
Thank you. Thank you, Chris and Felix. Bye-bye.
Bye-bye.
Bye, everybody.